Okay, so today we will be starting induction. So you have already done the experiment on induction, so you should have some idea about induction. But before we start, do you have any questions about previous subjects? About the previous subjects that we have, things that we had done until now. Sure. Every moving charge will create a magnetic field. Depends on how fast it is moving. If it is moving really fast, then it might be the magnetic field that it creates might be comparable to the applied magnetic field. But nevertheless, the force that it will feel will be only due to the external magnetic field. Well, we will discuss that experiment today. So then you can ask. First, let's discuss what is induction. Let's understand how that result comes about. I mean, if you remember, we had this long tube. When we put a magnet in the tube, it took really like 8 or 9 seconds to go through, whereas an ordinary object with a non-magnet just took less than 1 second to go through it. So first discuss what is happening there, and then we can ask what happens if we have a magnetic ring. So that's what you are asking, right? You have a magnetic tube, and then we send some metal through it. Other questions? Okay, so this induction thing we have kind of already discussed to some extent. If you remember, we had discussed this example. We had a region of uniform magnetic field. And then we had this rod, which was running on rails. And here we had some kind of a resistor R. So this was the thing that, the problem that we had discussed. And we assumed that this was moving with a velocity v in this direction. And so what is the force that this electron feels? Let's just take one electron in our rod. This is a conductor, one electron in our rod. What will be the direction of the force that this will feel? Well, let's see, V cross P is upward, the charge is negative, so the electron will be moving downwards. This is the force the electron will feel, and hence there will be a current in this direction. And the magnitude of the force that the electron will feel will be is charge times V times B. This is the magnitude of the force. So the amount of energy transferred to this electron as it goes from the top point to the bottom point, let's say this height is L, the work done on the electron will be EVB times L. This is the work done on an electron. But if you remember how we had defined an EMF, the EMF was nothing that the work done on a charge as it goes through the circuit, through some element in the circuit, like in the battery. So the battery, what it does is it takes some charge and gives energy to it and gives away some other charge at a higher energy. That's what the battery does. But this is what this system also does. So it takes electrons from this and gives out electrons at the other, and these electrons have a larger energy than the other one, than the electrons that entered into this system. And the difference in the energy is given by this one. Well, it is trying to go around, but it cannot go out of this wire. So it is confined here. So the actual movement of the electron will be, it will be try to go around, make a circle, but then it will hit the boundary, and then it will reflect back. So it will be making such a motion. Well, let's see. You see, what is happening here is as the electron is going around the circle, the magnetic field is not doing any work. But you see, it hits the boundary. When it hits the boundary, it will be reflected. It is exerting a force on this rod. So basically, that is what is doing work on our system, on the electrons. And since it is exerting a force, we have to exert some additional force on this rod to keep it moving. So we are basically doing the work, not the magnetic field. Magnetic field just acts as kind of a catalyzer, as a medium. It transfers our work. It allows the conversion of the work that we do on the energy of the electron. It doesn't itself do any work. Okay. Sure. We will discuss it in the next chapter. It does have some effect. Yes. But we will discuss those things later on. For the time being, let's just look at the first, in a sense, the first approximation. What happens due to this external magnetic field when this rod is moving. Okay. Now, you see, here, when you calculate the force acting on this wire, you see that it is in the opposite direction to the velocity. So if you just hit it, give it an initial velocity, then it will just slow down and stop. Well, that is due to the conservation of energy. No. Now, when we give it an initial push, there will be a current running through it, and the direction of the current is such that the force acting on this rod as a whole will be in the opposite direction. Okay, so let's see. This should be equal to E times EMF. So the EMF now the EMF, the electrons, there will be an EMF acting on the electrons only in this segment. The EMF along these segments will be zero. There is no force acting on the electrons due to the external magnetic field at least. So in general, we can say that this is the EMF of the circuit, of our system as a whole. Not just of this rod, but of this whole loop. This is the EMF of the loop. This will be VB times L. Now let's do one more thing. Let's say that this distance here is x. So the velocity v over here will be equal to the magnitude is dx by dt. Or let's say let's not take it all the way, let's take it only this way. Basically it will be the same thing. So this is equal to dx by dt b times L. But in this system at least, b and L are constant. So we can also write this as d by dt b times x times L. Now x times L is nothing but the area A. A is the area in the circuit where there is a magnetic field. This is the area where there is a magnetic field. So we have the B times the area, which is nothing but what we call the flux. So we can say that the EMF of the circuit is equal to the rate of change of the magnetic flux as a function of time. These are in terms of magnitudes only. These are only the magnitudes. Now, if we take into account the signs, there's also this sign. Okay, so the EMF in a given circuit, in a given closed loop, is nothing but the negative of the rate of change of the magnetic flux going through the circuit. Now, any questions up to here? Sorry? The direction of what? Now, I mean, you see, the flux is a number, it's not a vector. So you cannot say that the flux is in the direction of the magnetic field or not. So you see here what we have B times X times L. Let's go back to our figure. This is X. Look at here. This is X, this side. Height is L. So in this region, we have a magnetic field. We don't have any magnetic field over here. So X times L is the area in which there is a magnetic field. The magnetic field times the area is nothing but the flux. Well, this is basically the flux that goes through this area, but it is also the flux that goes through all of my circuit, because there's no flux over here. This is always minus. This is always minus. Always. Now we will see some applications of this minus sign. Now, any questions on this? Any other questions? You see, this minus sign will be important because of various things. I mean, when we are defining the flux, in general, we can write the flux as B times ds over any area. This is the flux in general. Now, in this question, we had assumed a uniform magnetic field. But this law over here is true for any magnetic field, whether uniform or not. But of course, if you don't have a uniform magnetic field, then you have to define the flux as an integral over the area. Now, when you are defining this area, you have to choose a direction for your, when you are calculating this flux, you have to choose some direction for your area, some positive direction. So if the magnetic field is pointing in some direction, it will contribute a positive to the flux. If it is in the other direction, it will contribute negative to the flux. So that is one thing you have to pay attention to. You have to determine the direction of the flux, the direction of the area element. Then when you are defining the EMF, EMF is nothing but the work done on a unit charge as it goes over your circuit element or around your circuit. So this is nothing but E dot dl around your circuit. So here you have an area. That area is bounded by your circuit. So you have that this area, the direction of this area, and the direction of your circuit has to be consistent. Again, just remember the right-hand rule. And once you choose these areas, then we have this minus sign. No, we didn't say B dot ds is equal to 0. What we said was B dot ds integrated over a closed surface. This is equal to 0. This is over a closed surface. So what this tells me that if magnetic field lines are entering a given region, they are also leaving the region. This is what this tells me. This also tells me that if you have this closed surface, if you divide it into two, let's say you have this closed surface, this tells me that you have, these are the magnetic field lines. It enters and leaves. Well, I can divide it into two. This is one surface. This is the other surface. They are divided into two. Here we have some flux. Here we have the opposite flux, depending on the chosen direction of the areas. So the flux at a given region, in this region, let's say, phi b is not equal to 0. But the flux around is close because the magnetic field lines pass through the surface in one direction. They do not pass in the other direction. But when you have a closed surface, if they pass in one direction, they have to also pass in the other direction. That's the difference. Other questions? Well, what was the definition of EMF? The work done per unit on unit charge as the charge moves around our surface, our circuit or circuit element. This is the work done is the force, the integral of F dot dl. The force per unit charge is the electric field. So as this rod is moving, there is an electric field building in our system, which is doing the actual work. Now let's apply this thing to the same example. Now, how do we use that sign? Now, first, this is our area, all of our area. This whole region is our area. What would you like to be the direction of this area? Now, you see, the area has to be either the area vector is perpendicular to our area. So it has to be either out of the screen or into the screen. Out of the screen. So this is the direction that we choose for ds. Now what should be the direction of dl in the EMF? Well, you see, ds and dl, they should be consistent with each other. They are not independent directions. Once you choose the direction of ds, you are already fixing the direction of your positive sense of your circuit using the right-hand rule. So, since this is the direction of ds, this is the direction of your positive dl. So this is the direction of our circuit, the positive direction of our circuit. So if we find a positive EMF, it means that as a unit charge is moving around this loop, it will be acquiring positive energy. If we find a negative EMF, then it will just tell us that if as a positive charge is moving in this direction, there will be a negative EMF acting on it. So if EMF turns out to be positive with this choices of directions, then the current will be flowing in this direction. If the EMF turns out to be negative, the current will be flowing in the opposite direction. So let's see, phi b. It is again b times L times x. Is it positive or negative? Positive meaning that the magnetic field lines are passing through this surface in the direction of ds. Negative would mean that the magnetic field lines are passing through this surface in the other direction. So magnetic field lines are passing in this direction, in that direction, sorry. The positive direction of this area is in this direction. So it's negative. So this is negative. d phi b by dt, well, b is constant, let's say for the time being, let's just study the case where B is constant. This is B times L minus dx by dt. Now, for the shown configuration, is this positive or negative? For this given configuration, we have this rod over here, it's moving in this direction with a velocity v. Now, is this positive or negative? Is this positive or negative? Now just look at this dx by dt. That's what I'm looking at. Is dx by dt in this system, is it positive or negative? Now dx by dt is negative because as time is increasing, x, this length, is decreasing. X is decreasing, t is, well, as time increases, x is decreasing. This is a negative number, this is a positive number. So this ratio is a negative number. With this minus sign, it makes it a positive. So this combination is positive. This is larger than 0. This negative sign doesn't mean anything, because there is this derivative which is negative. So let's see, this, the flux is increasing with time. Do you agree with that? Is this flux increasing? Okay, so the flux is? Yes. How come? Shouldn't it decrease? I mean, the area is increasing, flux is B times the area is decreasing, so B times area should be decreasing. It's a negative number, remember. So if initially the flux is, let's say, minus 5 Tesla meters squared, then as this is moving, it becomes minus 2 Tesla meters squared. Minus 2 is larger than minus 5. So the flux is increasing. Its magnitude is decreasing, but since it's a negative number, the flux itself is increasing. And finally, the EMF. This is minus d phi b by dt. This is less than 0. It just tells me that the current will not run in this direction. It will run in the opposite direction. That is what this minus, since this is less than 0, it tells me that the current will be running in the opposite direction to my chosen loop direction. Any questions on this one? Sure, you can do whatever you want after this point. Before the? Here. Well, you see, we have chosen a positive direction for our area. We had said that the area vector is pointing in this direction. So this is my area. I define an area vector which is pointing in that direction. Now that choice tells me that if there is a magnetic field line passing from this side to this side, independent of its direction, it will contribute positive. But if there is a magnetic field line that passes from this side to the other side, it will contribute negative to my flux. So we see here all the magnetic field lines are passing from this side to the other side. So all the magnetic field lines over here, they are contributing negatively to my total flux. That is why I put a minus sign over here. B is the magnitude. L is the magnitude. X is the magnitude. They are all, B, L, and X, they are all positive numbers. So BLX is a positive number, but I know that the flux is negative, so I just put a minus sign over there. Or you can also do it, if you want to do it more formally, let's say this is the direction of Z. ds vector is in the z direction. B vector is in the minus z direction. So B dot ds is equal to minus B times ds minus the product of the magnitudes. So this is the minus sign that appears over here also. We don't. Some of your friends, they wanted to choose ds to be in this direction. If we had chosen ds to be in the opposite direction, then the flux would have been positive. It's completely your choice. You chose this direction to be positive, so in this configuration the flux is negative. Well, let's see, does the current change? Well, we know that the current will be just epsilon over R. So does epsilon change? Well, we assume that B is constant, L is constant. So if the velocity is changing, then the current will be changing. If the rod is making an accelerated motion, then the current will be changing. Well, if it's moving faster, there will be a lot more larger current. If it is moving slower, there will be a smaller current. Well, just put the time dependence over here, then you will get the time dependence of the current. Any other questions on this one? True. Now let's write an explicit statement of this Lenz rule. The induced EMF opposes the change that created it. So this is, you can say, this is the Lenz law. In fact, this is why we have this minus sign over here. This minus, it just means it's trying to oppose. So if, let's go back to our example again, this one. This one. In this configuration. So this one is moving in this direction, so that is what is creating this induced EMF, the motion of this rod. Now we can say that as the rod is moving, the change in the flux, is it positive or negative? Again, using just this sense. The change in the flux is positive. Okay? So the EMF will try to oppose it. How? Well, you can say that it will try to create a flux that is in the negative direction. Now, how can it create a flux in the negative direction? What should be the direction of the current to create a flux in the negative direction? So if the current is running like this, you see here we have a magnetic dipole. And the magnetic dipole, if the current is running like this, the direction of the magnetic dipole is in this direction. And it creates a magnetic field in that direction in this circuit. So you were asking, what is the effect? Does this current has any effect? Well, this is one of the effects. So there is a magnetic field. So there is some flux in this area. As this rod is moving, the flux in this area is being reduced in magnitude. So the current should be such that it will try to increase in magnitude this flux. And that is possible if there is a current running in this direction, because if there is a current running in this direction, it will create some magnetic fields pointing into the screen in this region. Well, the magnetic field lines in this region will be pointing out, but we are interested in this one. So it will create a magnetic field into this region, into the screen, and hence increase the net flux in this area. Now, this is one way of using the Lenz law. Another way, well, you can say, okay, the current, the reason why we have this induced current is the motion of this rod. So the rod is moving. So that is the change that is creating this EMF. If the rod was not moving, there wouldn't be any EMF. So how can you oppose this motion? By creating a force in the opposite direction. So the current should be such that the force acting on this rod should be in the opposite direction. So if this is the current, what is the direction of the force acting on this rod? In the left-hand side. So the force acting on this rod will be in the opposite direction, and hence it will reduce this effect. This current will reduce this effect. Any questions on these? Yes, if you want to keep this moving at constant velocity, you have to keep pushing it. Now, if there is no magnetic field, you just push this rod. In the absence of friction, it will just keep moving. But now, in this case, you have to keep pushing it because we have a magnetic field and there is a current running through the system. You see, if this wire was absent, in that case, it will just keep moving. You don't need to exert this force. But the presence of this circuit causes it to slow down. Because what will happen is there is a current running through it, there is a resistor over there, that resistor will dissipate energy. That energy should come from somewhere. And where it comes from is the kinetic energy of this rod. The kinetic energy of this rod is converted into electrical energy, which is then dissipated through the resistor as, let's say, heat or as light. Now let's come to this aluminium tube. If you remember, this was our tube. And we put some magnet in the middle. Let's say this is the north pole, this is the south pole of the magnet. This is aluminum cylinder, aluminum tube. Now, by the way, before passing to this example, now one nice thing about this Lenz law is that if you look at this example, we say that, okay, this volume is moving in this direction, this rod is moving in this direction, so that we have this EMF created. But if we go to a reference frame in which the rod is at rest, well, the rod is not moving, there will be nothing due to these things. Due to these wires, well, in that reference frame, these wires will be moving, but their motion will not create any current, any EMF. Because if you have let's say, the wire is moving in this direction, what will be the direction of the force acting on the electrons? Upward. It will not be along the wire, the electrons will not be able to move, so nothing will happen if we stick with this description only. But in this law, this law is more general in the sense that even in that new reference frame, if we go to that new reference frame, you see the magnetic field lines are now moving. Since they are moving this area, it will get smaller. Even in the reference frame in which V is at rest, in the rod is at rest. So the flux will still be changing. If the flux is changing, still we will get an EMF. So that this law is still valid. This is still valid. Whether we are in a reference frame in which the rod is moving, or we are in a reference frame in which the rod is at rest. Now, why will it be important? In this example, it will be important because in this example, we have the magnetic field that is moving, not the conductor. The conductor is our aluminium tube, it is at rest, but the magnetic field lines are moving. So let's just imagine this ring over here. This is our ring. What will be the direction of the current on that ring as the rod is moving? So first of all, let's just choose a direction for our ds also. Let's say ds is in this direction. So what is the direction of dl, sorry. Right hand rule, this ds. So this is the direction of the positive current. If EMF is positive, then the current will be running in this direction. So is the flux, what is the sign of the flux? Positive or negative? Positive or negative? What's the direction of the magnetic field? Well, it is more or less in the up sense, either in this direction or in that direction, but mainly on the average it's upwards. ds is downwards, so phi b is less than 0. So these are our magnetic field lines. So the magnetic field in this area is pointing upwards. ds is downwards, so flux is negative. Does the magnitude of the flux increase or decrease as the magnet is approaching? Well, if you are far away from the magnet, the magnetic field is small. If you are close to the magnet, the magnitude of the magnetic field is larger, so the flux, the magnitude of the flux is increasing as the magnet is moving down. Phi b, the magnitude is increasing, which means phi b itself is decreasing. Sorry? So, you see, if in the definition of the flux, I don't care about the velocity. This is the definition of the flux. It doesn't depend on the velocity. It's a number also. Well, of course, it will affect because it will change how the flux is changing. If the magnet is moving fast, then the flux is changing fast. If the magnet is moving slowly, then the flux will be changing slowly. But it doesn't affect the flux itself. It affects how the flux changes. The only thing that the flux depends on is the distance of this area from the magnet. That's the only thing that this flux depends on. So flux is increasing. So what will be the direction of the EMF? Or let's put it in this way. d phi b by dt is less than 0. EMF is positive. So that is the direction of the current. The current will be running in this sense. Well, we can also use the Lenz law. You see, the magnetic field here is increasing in the upward direction. The magnitude is increasing, it's in the upward direction. So that's how the magnetic field is increasing. The change in the magnetic field is upward. So the current, induced current, should be such that it creates a magnetic field downward to keep the magnetic field constant, or try to keep the magnetic field constant. So to create a magnetic field in the downward sense using the Lenz rule, the current should be in this sense. So run in this direction so that it creates a magnetic field in the downward sense direction. Why? So, you see, this is aluminium. It's not a ferromagnet. If it was a ferromagnet, it would have a strong influence of these magnetic field lines. But since it's not a ferromagnet, it doesn't have such an effect. Okay. Well, we can do the same thing here, but if we want to use the force concept, magnetic force, we have to go to another reference frame in which the magnetic fields are at rest. So we just go to a reference frame in which we are also moving downwards with the magnet, so the magnet is at rest. This ring is moving up. So if you take an electron over here, the magnetic field at that point is somewhere in that direction. That's the direction of the magnetic field. The electron is moving in that direction. So V cross B will be a vector in that direction. Well, the electron is a negative charge, so it will feel a force in the opposite direction. This is the direction of the force of the electron. So the electrons at this point will feel a force in this direction. Electrons will go around like this. But that means the current will be running in this sense, exactly in the direction that we have found. So you have all these various points of view looking at the same problem. And they all give the same answer. They should give the same answer. So you can either you can use this Ampere's law, or Faraday's law, or you can use the Lenz rule, or you can just look at the forces acting on an electron in some different reference frame. The direction of the magnetic field. Here. But I'm looking at an electron over here, so the only thing I care is the magnetic field at that point, which would be tangent to this magnetic field line, which should be in that direction. So here I have a ring, or let's see, let me draw this system again. This is my tube. This is my magnet. This is the North Pole. This is the South Pole. And the ring is falling down. The magnet is falling down. And we have just said that the current will be like this. Or on the surface that is visible to us, we will have such a current on the bottom side. On the top part, we will have a current in the opposite direction. No, it does touch. I mean, here just, if they touch, I mean, it will be hard to sketch it. It will touch. So, we have this magnet. Here, these loops, this part will also behave like a magnet. And what is the North Pole of that magnet? Where is the North Pole? You see, this is the direction of the currents are running in this sense. Okay, so this will be how the magnetic field lines created by this part will look like. They will just look like this. That means, okay, this is the direction. This is the North Pole. This is the South Pole of this magnet over here. This just behaves like a magnet, this part of the aluminium, and this is the South Pole of that part, this is the North Pole of that part. Now, if you look at the top part, the current is running in this sense. That is like this. What is the North Pole? North Pole is upward, the South Pole is downward. So we can just, in a sense, in a simplified picture, we can divide this system at this instant into 3 magnets. One is the original magnet. These two are nothing but the parts of this aluminium tube. So you see this South Pole and the South Pole of magnets, do they attract or repel? They will repel each other. The South Pole and the North Pole, they will attract. So both of these magnets will exert a force on our original magnet in the upward direction, the opposite direction to gravity. So that is why it is slowing down. And okay, so if this force due to these induced currents is smaller than the smaller than the weight of this magnet, the magnet will start moving faster. But if the magnet is moving faster, it means the flux will be changing faster. So the EMF will become larger, and hence we will get larger currents. Larger currents means that the magnetic force acting on the magnet will be also increasing. It will keep increasing until the gravitational force acting on the magnet is equal to the magnetic force acting on the magnet. So it will just move at constant speed. And this is why it is just slowing down until it reaches some constant speed, and once it reaches its constant speed, it just keeps moving at the same speed with 0 acceleration. And this is why it takes such a long time for the magnet to fall down. Well, let's see, the currents are running like this in the top magnet. So how does the magnetic field lines look like? So in the center they go up, and then they go down. North pole of a magnet is nothing but the point through which the magnetic field lines come out. So that is why we have this North Pole and the South Pole. Any other questions? Well, nothing is discontinuous, so the current will be largest here and there, so it will get smaller as you go away from the magnet, and as you go from this point to this point, the current will get smaller and smaller. At some point it will be 0 and then just change its direction and start growing up. Now, it's not so easy to see it as these ones, because you have both the magnetic field line that is going through the magnetic field lines outside, but nevertheless the idea will be the same. The current will more or less go like something like this. Oh, sorry. It will look something like this. This is where we have the magnet. Other questions? Well, you see, if the magnetic force acting on the magnet is smaller than its weight, it will start accelerating. It will keep on accelerating, right? So the magnitude of its velocity will be increasing. But if the magnitude of the velocity is increasing, it means the fluxes, the change of the flux, which depends on the velocity, will also increase. If the magnet is moving fast, the flux at a given area will be changing fast. If the flux is changing fast, that means the EMF will be fast, EMF will be larger. If EMF is larger, then these induced currents will be larger. But if the induced currents are larger, it means there will be a larger force acting on the magnet. So the magnetic force acting on the magnet will get larger as long as the magnet is increasing its speed. But there will eventually come a point, if the tube is long enough, there will eventually be a point at which the magnetic force is equal to the gravitational force. At this point, the velocity will be constant, the rate of change of the magnetic field will be constant, the magnetic flux will be constant, EMF will be constant, hence the currents will be constant. So nothing will change after that point. What will change in this argument? Or if the tube is made of a magnet and you have this thing is made of aluminium, just repeat the arguments. Is there a change in the flux in the system? Does it induce new currents in the system? Does these new currents will always try to prevent the change? So you see, you can apply, to determine the direction of the force, you can also use the Lenz rule, which says that the induced currents will be such that they will try to prevent the change. So it will be such that these currents will be such that they will exert a force on the magnet in the opposite direction. And that is actually what we see over here in this more detailed analysis. Okay, let's give a 10-minute break and see you after the break.